Have you ever wondered how we could teach a computer to see the world not just as, a bunch of objects, but to understand the exact shape and boundary of every single thing in a picture? To see not just the dog, but the actual outline of its fur against the grass? Well, that's exactly what we're going to dive into.
And really, this question gets right to the heart of it. I mean, why do we even need this? For some things, sure, a box is fine. But when the stakes get really high, think about a self-driving car that needs to know the exact edge of a person, or a robot performing surgery. Good enough just isn't good enough anymore. You need absolute, pixel-level precision.
And this visualizes the difference perfectly. On the left, you've got the old way, a simple bounding box. Yeah, it tells us there's a dog there, but it also grabs a whole bunch of the background grass. But then you look at the right, and that's something else entirely. That's a pixel-perfect outline, a mask. It's the difference between knowing about the dog and truly seeing the dog.
All right, so to really appreciate just how big a leap this is, we first need to understand why that simple box, why it just wasn't cutting it. So, the classic approach is something called object detection. It's actually really powerful, and it's built on answering two really simple questions. What's in the picture, and roughly where is it? The output is pretty straightforward. You get a label, like dog, and it draws that familiar rectangle around it. And for a long time, that was a fantastic starting point. But, as you can probably guess, these boxes have some serious limitations. I mean, they're just rough approximations, right? We saw it with the dog. They grab chunks of the background, and they tell you absolutely nothing about the object's real shape. For so many of the advanced applications we're dreaming up, we needed to do a lot better. And that leads us to this really revolutionary idea. What if, instead of drawing a clumsy box around an object, we could teach a computer to color inside the lines just like we do, to actually understand an image, pixel by individual pixel? And honestly, this analogy is just perfect. Image segmentation. That's the name for this incredible technique. It doesn't just put a box around the dog, it assigns a label, in this case, dog, to every single pixel that actually makes up the dog. This is a massive, massive leap from a box-level understanding to a true pixel-level understanding of the world. Now, as it turns out, there are two main ways that computers can color in the world. First, you've got semantic segmentation. This one finds all the pixels of a certain class, say sheep, and colors them all the same. It just knows sheep are here. But then there's the more advanced version, instance segmentation. This doesn't just find all the sheep, it identifies each individual sheep. And boom, this picture just nails the difference. On the left, with semantic segmentation, the computer is basically saying, I see a bunch of sheep. All the sheep pixels get lumped together. But look at the right. With instance segmentation, the computer says, I see 4 distinct sheep, and it gives each one its own unique color. It can count them, it can track them. It's a whole new level of understanding. So, how did we even get here? How do you teach a neural network to do something so detailed? Well, the first major breakthrough was a really clever network design, but it came with a super frustrating problem. So the big idea came from something called a fully convolutional network. And here's the simple version. The network first shrinks the image way down. It's kind of like squinting to get the general gist of what's inside. Then it tries to blow that understanding back up to the original size to make a prediction for every single pixel. But here's the catch. You know what happens when you take a tiny thumbnail photo and try to blow it up to full screen? It gets all blurry and loses its sharp edges. Well, the exact same thing was happening here. That process of shrinking and then re-enlarging the data, it was losing all the fine details, resulting in blurry, imprecise outlines. So, how do you solve this blurry vision problem? How do you get both the big picture understanding and all those fine-grained details? The answer came from this absolutely brilliant architecture called U-Net. So the U-Net has that same shrink and expand structure, but it adds a stroke of genius. As it's shrinking the image down on the way in, it saves the high-resolution details from each step. Then, as it's expanding back up, it uses these special skip connections to bring those saved details back into the process. It's like taking super detailed notes while you're squinting, then using those notes to draw a much sharper picture later on. And that right there is the magic formula. It gets the what, the high-level idea that, yes, this is a dog, from those deep, compressed layers. But it gets the where, the precise location of the dog's fur, from the shallow, high-detail layers it saved. Combining those two is what finally gave us those crisp, accurate segmentation masks we were looking for. Okay, so we've cracked the blurry vision problem. We can now give computers this sharp, pixel-perfect sight. So what can we actually do with it? Oh, this is where it gets really exciting. And in the real world, this kind of precision can literally be a matter of life and death. Take medicine, for instance. Being mostly right about the location of a tumor could be a disaster. Image segmentation allows an AI to outline the exact shape of that tumor, helping doctors with diagnosis and surgical planning with a level of precision that a simple box could never, ever provide. And of course, the technology just keeps getting better. State-of-the-art models like Mask, RCNN basically combine the best of both worlds. It's so clever. They work in 2 stages. First, they use fast object detection to quickly draw boxes around everything that might be interesting. Then, and only then, inside each of those boxes, they do the heavy lifting of generating that beautiful, pixel-perfect mask. It's both incredibly fast and super accurate.
So we've gone from these clumsy, rough boxes to basically giving AI its own digital coloring book, letting it understand the world with this incredible granularity. And that leads to this final, fascinating question. What happens next? What does the future look like when every single pixel in our world becomes machine-readable and truly understandable?